Assalamu alaikum and good morning everyone. My name is Abdullah and my supervisor is Dr. Marshid Hanafi, and I am going to present you today a deep learning based chili plant growth monitoring system. In this presentation we will go through introduction, problem statement, objective, scope, literature review, methodology, and the experiment and results. We'll go through data collection, data augmentation, manual segmentation, training and testing, age identification, and system measurements, and finally conclusion. Introduction. The cultivation of crops in greenhouses under specified conditions has received great attention due to the high food demand by the increasing population. The chili plant growth monitoring system in Malaysia still performed manually by human laborers, which consumes lots of time, energy, and the plant growth can be monitored at site. Convolutional neural network (CNN), one of deep learning approaches, has become a powerful tool for tackling images problems and can even instantly detect and separate objects from complex background. Being able to monitor the growth of plants using CNN-based methods will eventually help to achieve two major goals. The first goal lies in achieving maximum growth rate while lowering necessary energy consumption and providing an opportunity to monitor the growth rate as a function of environment conditions. The other goal is associated with the growth control and the fruit production. By monitoring growth rate of every individual plant, one can easily check plant health and find out abnormals, which leads to better estimation of fruit quality and the final production. The problem statement touches four main points. The study of the automatic chili growth monitoring in greenhouses has not been properly investigated in Malaysia. The growth of chili plants is monitored manually by human laborers. The process consumed lots of time and energy, and the monitoring can only be performed at site. The objectives of this study is to identify the methods to develop the proposed deep learning-based chili growth monitoring system, to design and develop the proposed system, and lastly, to evaluate the performance of the system. The scope of this study will be by developing the proposed system and evaluate the performance of this system. In the literature review, we will go through previous methods of deep learning, image segmentation, and two scenarios of transfer learning. The first method of deep learning was proposed in 2014, which was called RCNN, and these are the papers that worked on this method. Later in 2015, fast RCNN was proposed, and it is the development of RCNN. Then in 2016, faster RCNN was proposed, and it is the development of faster RCNN. Other approaches such as you only look once and single shot multi-box detector, both of these approaches were proposed in 2016. And as a summary of these approaches, RCNN was slow at time. Fast RCNN needed external measure proposal approach. Fast RCNN had a good balance between accuracy and speed. YOLO, you only look once, was fast. Single shot multi-box detector was the fastest. However, it performed poorly with the smaller objects. And the original proposal generations for these approaches was selective search for both RCNN and fast RCNN. Regional proposal network was with the faster RCNN. YOLO takes the whole image and processes it instead of regional proposals. Single shot multiple box detector estimates proposal generation with all computation in a single network. And the higher accuracy, as you can see, is for faster RCNN, 76.4%. Image segmentation, we have two approaches for image segmentation, semantic segmentation and instant segmentation. Semantic segmentation was proposed in 2016, and these are the papers that working on this method. And instant segmentation was later proposed in 2017 with mask RCNN. Mask RCNN was proposed in 2017. It was the development of faster RCNN. It's the approach of instant segmentation and object detection. And this method has an extra branch for predicting segmentation mask. Mask RCNN can be applied for other tasks than object detection. And mask RCNN method outperform all current methods and community in all three tasks of COCO challenge, instant segmentation, object detection, and person key point detection. Transfer learning. It needs a huge amount of data to train a model from scratch. So in transfer learning, we can use a pre-trained with a huge amount of data CNN network and retrain it for other classes with a fewer data set. The first scenario uses CNN as fixed feature extractor by removing the last fully connected layer and then treat the rest as fixed feature extractor and only retrain the classifier. The second scenario aims to fine-tune the CNN. This strategy is to not only retrain the classifier for a new dataset, but also fine-tune the weights of the pre-trained network. Methodology. Mask RCNN architecture, as you can see in this figure, has two stages. Both of the stages are connected to the backbone structure, and the backbone consists of two main networks, which are, in our case, either ResNet 50 or ResNet 101 with a feature pyramid network. The first stage generates a proposal about regions where there might be an object based on the input image. Second stage predicts the classes of objects, refines the bounding boxes, and generates masks and pixel level of objects based on the first stage proposal. The first stage is a lightweight neural network called regional proposal network. It scans all feature pyramid network and proposes regions which may contain objects. RPN uses sliding window method to produce anchors. Anchors are set of boxes, predefined locations and scales relative to the input image. Ground truth classes and bounding boxes are assigned to individual anchors according to the sum IOU interest of unit value. And the interest of unit value is the ratio of how much of an object is detected in an anchor. As anchors with different scales bend to different levels, the feature map RPN uses these anchors to figure out where of the feature map should get object and what size of its bounding boxes is. The second stage, the region of interest network, is another neural networks which take the proposed regions by the first stage, the RPN, region proposal network, and assign them to several specific areas of feature map level. It scans these areas and generates objects, classes, bounding boxes, and masks. The procedure looks similar to RPN. The differences are that it's without the help of anchors. The second stage used a method called region of interest align to locate the relevant areas of feature map. Experiment and results. The first stage in experiment and results is data collection. We use to capture images, smartphone, iPhone 8. The chili plants were detected, were captured, were the images of these chili plants were captured in week 10 and week 14. The images were taken, as you can see in these images, from side view and top view. The distance for side view, the distance between the camera and the chili plant was 1.5 meters and 2.3 meters for top views. For data computation, to get as much as images for training and testing of the models, we applied some effects for side view images. We applied a mirror effect. As you can see, the image on the left is the original, an example of the original side view image of chili plant, and on the one on the left is the mirrored image, and the last image on the right is the image that brightness changing effect applied on it, which is darker image. And all of these images were resized to 1024 pixel by 1024 pixel. And for top view images, effects mirror brightness changing and rotation by 90, 180, and 270 degrees were applied. As you can see, the top left image is the original image, and an example of rotation by 180 degrees is the top image on the right, and the bottom left image is the mirror effect of the original image of top view chili plant. And lastly, the darker image of top view chili plant is the bottom on right image. And all of the images are similar to the size of side view images were resized to 1024 by 1024 pixels. And the total number of images, you can see it in this table, which is 256. And you can see in this table all the images for each class and for each effect. Manual segmentation. In order to establish the classes, the grounded truth classes, and mask, we have used image attenuation tool VIA to do this, and you can see these two examples of side view and top view images that we have worked. Training and testing. For training and testing of models, we used a laptop with Core i9 and memory of 32 gigabytes, and with GPU of GTX 1650 with graphical memory of 4 gigabytes. Software that was used Python 3, Keras, and TensorFlow. The training box loss, as you can see, both models reached 0.01, and the training class loss both of them of models was also reached 0.01%. And the validation box loss uh, was for ReasNet 50 model about 40% and 35% for ReasNet 101 model. And for mask RCNN ReasNet 50, the model was about the lost class or about 24%, and the model of ReasNet 101 was about 16%. And note that the images, the number of images that was used for training was 75% of the total data set, and 25% for testing. And number of epochs was 17, and epochs is how many numbers that the model will retrain itself with this data set. And the number of steps was equal to the total number of images in our data set, which is 256 images. The age identification. We have applied all of the 256 images to both of the models, and in ReasNet 101, mask RTNN ReasNet 101 model, the accuracy, the total accuracy of the detection was 96%, with some problems that we will talk about it later. And in ReasNet 50 model, the accuracy was higher than ReasNet 101 model by 1% point 25. And the accuracy is 97.25%, as you can see in this table. The problems that we had for model mask RCNN ReasNet 101 is that in week 14, the detection of the fourth plant in the top view was detected as week 10 and week 14 at the same time for some times, and other times it was detected correctly. And the problem that we had with both of the models, some plants in week 14 in the side view was not the models were not able to detect it at all. And some other times the detection was correct, as you can see in these images. For chili plants, height and tree crown measurements, we need first to measure the actual size of each pixel in these images, and we used ImageJ free software to do this. And as you can see, we need to measure the actual size for side view and top view separately, because the distance that were captured, these images captured different. So we used the height of the boundary box to, as you can see in the left image, we used the boundary box height to measure the height of the planet, the chili plant, and we used either the largest value of either the width or the height of the boundary box to measure the tree crown of the chili plant. The differences between the manual measurement and the system measurements, as you can see in these figures, for height in week 14 for both of the models. For ReasNet 50 model, the error was about 15 centimeters, and for the maximum error was 15 centimeters, and the maximum error was about 6 centimeters for mask RCNN ReasNet 101. And for the measurement of tree crown in week 14, ReasNet 101 achieved maximum error of around less than 14 centimeters and around 18 centimeters with ReasNet 50. And the maximum error was for height in week 14 was about 11 centimeters for ReasNet 50 and 9 centimeters for ReasNet 101. And the maximum error in week 14 for tree crown measurements was about 16 centimeters for ReasNet 15, and ReasNet 101 achieved error of 14 centimeters. And as you can see, for overall in these figures, the performance of mask arsenal ReasNet 101 is much better than mask arsenal ReasNet 50. In conclusion, we have designed and developed chili plant growth monitoring system based on mask arsenal and deep learning approach. And we have evaluated the performance of the system for both of models, ReasNet 101, 101, and ReasNet 50. And these are the references that we used to do the slides. Thank you all for listening. Thank you very much.